So our next talk is on multi-threaded concurrency efforts, and it will be presented by Quincey, that Elena already introduced, Quincey Koziol from Lawrence Berkeley National Lab, and my coworker, Chris Hogan from the HDF group. So if you guys want to go ahead and get started.
Yes, thank you, Lori. So as Elena and I think Mike mentioned, my name is Quincey Koziol. I'm currently at the National, oh gosh, what does NERSC stand for? Scientific Computing Center. It's a DOE facility at Lawrence Berkeley National Lab. And Chris Hogan at the HDF group and I will talk through some of the issues around making HDF5 more concurrent and thread safe for multiple threaded concurrent access. So with that in mind, this jumps in a little bit, so maybe I will flip back to this current concurrency control in HDF5. This is the way things are done now, right? An app will come in with multiple threads into the HDF5 library. It'll attempt to access things, and there is a single global lock around all the data structures in HDF5, and that global lock guards the access to those data structures. So only one thread will be allowed into the library at a time, and therefore thread safe, but no concurrency. One thread at a time, it'll go in, finish whatever it was doing, gigabyte-sized I/O, teeny tiny little, update a property, whatever. Only one thread comes in and then has to leave, and then another thread will, acquire the lock and come in and do whatever it was planning to do. So what we'd really like to do is allow the app to have multiple threads entering HDF5 and then performing concurrent progress through the internals of the HDF5 library, all the different data structures in there, and those data structures themselves will be guarded with individual locks or mutexes, and therefore much more concurrency. There'd be finer grain locking, and many threads can be executing, and yes, a thread might have to wait for another thread to lock and unlock a data structure, but that access time, the latency, will be much, much, much lower. So going back to my earlier slide, we'd really like to see this fully concurrent execution of all HDF5 API routines for multiple threads. That's the big picture, long-term goal, right? Immediately, what we'd like to do is make at least one API routine, a single HDF5 API routine, thread safe and fully concurrent for its primary function, possibly under limited circumstances. For example, the one we're going to use in this talk is fully concurrent execution of a dataset read, H5D read call for multiple threads all the way from the API down to the actual POSIX read call in the virtual file driver. That main path will be fully concurrent and multiple threads can be executing along it. I'd also like to see us take a breadth first, because that's kind of depth first, but a breadth first down to a certain appropriate level of many HDF5 API routines. And for example, it'd be really nice if the virtual object layer routines, the routines that deal with objects in files, were concurrent at least down to issuing the callback to the virtual object layer connector. So that would allow, say, a non-blocking access down to the virtual object connector. And then the connector could have the chance, at least, to queue up things for background execution, such as an asynchronous execution. And we'll talk tomorrow about vol connectors and how to make those things happen. But that's another really valuable use case, I think, for this multi-threaded concurrency effort. So focusing today, we're going to go back to the dataset read goal. And our goal is to eventually get all the aspects of the library to look like this, right? But starting with a multi-threaded safe dataset read with some constraints, right? We accept that it would be very complex to make every form of HDF5 dataset, multi-threaded concurrent from the very beginning. So we're just going to focus on contiguous dataset layouts. So no chunking, no external storage, no virtual datasets, fixed length data types, so not strings or vectors of ints and things like that. You can't do type conversions. So, you know, endianness and int to float transforms will be out. We have this data transform capability that allows you to do sort of linear transforms of data values. Think Fahrenheit to Celsius conversions, basically. And this is going to be serial, right? We're only going to go down to the POSIX virtual file driver inside HDF5, so it won't be supported for parallel MPI applications. We do want it to, you know, operate correctly. The same multiple threads to the same data set or multiple threads to different data sets, so that should be fine. And we'd like to handle the errors correctly, right? You know, if something bad happens, we don't want the multi-threaded scenario to blow up and crash or corrupt your data or anything else like that. So with that picture in mind, this is kind of what we're going to accept as our constraints for the first set of enhancements to make things multi-threaded safe. Chris can jump in here and I'll switch slides, but he can tell me what to do about the experiments that he's performed down this direction.
Thank you, Quincy. So with the goal of making H5D read multi-threaded, I'm going to describe the initial experiments that we did in that direction. So the basic idea is, first we have to get rid of that global API lock from H5D read so that more threads can enter the library. That will reduce the lock granularity, but we still have to make sure we're protecting all the shared data. So there will still be locks. And basically for this first version, we just push that global lock down into functions that are called after entering H5D read, but before getting to the bottom. I'm hearing my audio is quiet. I'll try to speak louder.
Okay.
So yes, we push the global API lock down into functions that are called in between H5D read and the bottom of the stack, which is pread. So there is some serialization still in there with this scheme, but the main point is that multiple threads are calling pread. In addition to the constraints that Quincy described on the last slide, we have a few more just to make this experiment as simple as possible. So first, I wasn't dealing with error handling in this version, so I'm assuming no errors are encountered. But for the final version that ends up in the library, sure, we have to make the error handling thread safe. But for this version, no error handling. We're assuming all library initialization is complete before any thread calls H5D read. So a main thread will open a file, open the data sets, and synchronize with the worker threads so that no thread is doing anything except calling H5D read while multiple threads are active, because we only have this one call thread safe at the moment. So for example, if one thread is trying to open a data set while another thread is trying to read from a different data set, there could be issues. So right now, initialization, synchronization, read, synchronization, finalization. Additionally, we disabled the free lists. Again, this just reduces the code paths we have to analyze. So normally the library will try to reuse memory, and that will need some multi-threading work done. By disabling the free list, we're just using malloc and free, so those are already thread safe. And additionally, we define in debug, again, just to reduce the amount of code we have to look at. So no assertions, no error checking. It just makes the analysis easier. The test program that we were working with was a main thread opening an HDF5 file. The file is very simple. It's just 8 data sets. Each data set is 64 megabytes. and I believe they're 64-bit integers. So the main thread opens that file, initializes the library, opens the data sets, and then spawns worker threads. The worker threads each read one data set. So the case I'm describing, we have N threads reading N data sets, but this also works for N threads reading one data set. And after that, we synchronize, because again, if one thread is trying to close a data set, that could mess with some global shared data, so synchronize, and then the main thread does all the closing and finalization and then exits. And really, we're just looking at how viable our idea is, how difficult it is, how hard is it to go through and make sure everything is thread safe. And yeah, how much work is that? So here are the results from that experiment. This is on Cori at NERSC with Lustre. The first graphic is the current status of things with the global API lock. You can see the dark green rectangles are running threads. So the work is completely serialized. Only one thread is running at a time, and all the other threads are waiting for that, which is, yeah, it's thread safe, but it's not concurrent. And the second picture is after the work we did of pushing the global API lock down further into the library. Here you can see that we have all threads running at the same time with minimal context switches. So a picture is worth 1,000 words. There's not much more to say about that. It looks pretty good. There's obviously a lot of concurrency. So the next step is kind of to take this this test code and kind of fortify it a little more so that it's ready to go into the library, because we need to remove several of the constraints like error checking and things like that. But it's promising so far. I'm not looking at well time actually for this. I'm just focused on concurrency. There's a question about time. Yeah. So yeah, no wall time. So this is a fast program, and actually the locking here is still really coarse-grained. There's still a lot of serialization in the library, but since for this program, all of the time is spent in p-read, all we care about is getting multiple threads doing p-read. Now, once we start opening up more features, we will have to fine-tune those locks. Once we have more complicated files with deeply nested groups, then we will need more fine-grained locks for more concurrency. But in this initial case, it didn't require much actually for locking. That's all I have. So I'll give it back to Quincey.
Super. Thanks, Chris. So returning back to this is where our community effort from myself and Lee Ward at India National Lab are planning to build on Chris's work and take that into the next step of productizing it effectively with these constraints, but making certain that an application can, as long as it stays on this golden path, if it was dealing with a data set that met those constraints, would get fully concurrent access to data sets through H5D read. There's a ton of kind of internal infrastructure here. I'm just going to kind of call out the high points. We need this recursive and lock, but it has to be a reader's writer's lock. If you know your thread safety terminology, that'll mean something for you. There's a bunch of internal HDF5 implementation that needs to get updated, all these macros that we work to keep this code in nice, high quality and easily maintained, but they were never designed with thread safe concurrency in mind. So they need to all get updated along the way. Basically, all of this is internal guts of the library that has to get put into place before we can make any improvements to actually opening up the dataset read call or other API calls for multi-threaded concurrency. We sort of view this as paving the way for community contributions, right? We don't have enough time. Me and I, we're going to do this first set of work to modify the dataset open and read and close paths, and probably the internal aspects of the ID management that's inside the library. We'd really like to see other contributors come in and help open up other code paths for follow-on patches and additions to this, so they would be able to enable multi-threaded concurrency throughout the library. We'll get the infrastructure in place, we'll do some good examples, and we'll get started, but clearly there's a lot of code. It's 400,000 lines of code in the library. Much of it is going to need to get touched in order to become concurrent. So hopefully others can leverage this strategy and use our code as examples. We see an obvious, nice place for a community contribution for the memory allocation routines inside HDF5. Chris mentioned that the free lists were turned off. Lots of threads can serialize up here, and it would be great to have a contribution or another collaborator to work on that aspect while we were working on other things. We really think that this should be very technically sound. It's very incrementally achievable, right? Once we get the infrastructure put into place, everyone can come in and say, oh, I see there's this hotspot here. This place could really use some better concurrency. I can tackle this small, localized, incremental improvement, and then build a test on top of that that shows it's working correctly. Our code, we'd like to make certain that it's production quality, it reduces the technical debt, it builds that infrastructure, and it's an example. So we're planning to do this, and then open up the forum, the floor for others to contribute and collaborate about things like that. So any more questions here? I've got a couple of minutes. We can chat about thread safety and how you'd love to have one thing or the other. I will stop sharing. Well, I'll go back here and we can chat and talk about other things. So, question from Mark Miller. Do you happen to have an ordering of API modules prioritized? I think that's a great thing to come up with, Mark. We can produce at least a first draft of what the right set of API layers to tackle are. That was part of the reasoning for that ID manager that I mentioned. That's very near the top, and lots of people will bottleneck around it, and it's a common routine. We'll tackle that first. Any other questions, comments? Oh, okay. Larry, I can give it back to you a couple of minutes early.
There is one, Quincy.
Oh, another one, sorry.
Yes.
John Reedy, contiguous dataset restriction apply to just the SEC2 driver. Well, they're sort of orthogonal contributions. Contiguous data could be accessed with the MPI driver, for example. But we're trying to reduce the code paths that we have to cut through in order to get the locking simplified enough. So right now we're just thinking about the native HDF5 vol connector, and that means a whole bunch of things, one of which is we can choose contiguous and the POSIX virtual file driver at the very bottom. The other vol connectors are effectively almost entirely in a different domain. It goes back to this first slide that I mentioned. I don't know if I could share back for a minute. Where I mentioned that it would be really valuable to have multiple concurrent access to the vol layer. If we can get the HDF5 API to be thread safe down to the callback for a vol connector, then we can turn it over to the vol connector, and it would have to implement thread safety, but it can do whatever it would like at that point. So that's where John's question about the REST vol connector comes in. We get it thread safe down in a breadth first way down to here, then any vol connector will get concurrent access from multiple threads.